Sometimes we're going to have two different samples of numerical data. And further, the data between these two samples, it comes in pairs so that each number in one sample corresponds to one particular specific number in the other sample. And further, these pairs of numbers are strongly correlated. If one is large, then the other is likely to be large. If one is small, the other is likely to be small. So, for example, what would be examples of this? Like, suppose I want to study a particular diet and see how effective it is. So what I'll do is I get my subjects, I randomly select my subjects, and then I measure all their weights before the diet, and then they do the diet for a couple months or something, and then I measure all their weights after the diet. So my two lists of numbers, the before and after weights, they correspond so that, that's this person's before weight and that's this person's after weight. Another example would be, suppose I want to study whether do mental relaxation exercises help you to solve puzzles more effectively. So what I do is I gather my subjects, and then I give them a puzzle, a word search, a maze or something like that to solve on pencil and paper. And I measure the amount of time it takes them to do that. And then I have them do a few minutes of mental relaxation exercises. And then I give them a similar puzzle. And I measure how much time it takes them to solve that puzzle. So now I've got a list of numbers, the times before the mental relaxation exercises and the times afterwards. And I want to see if these make any significant difference or not. Another example would be, I want to compare textbook prices on Amazon.com versus the university bookstore. So what I do is I look up the prices of all these textbooks on Amazon, and then I look up the prices of those exact same textbooks on the university bookstore. So I find the price of this textbook at the university bookstore, and then the price of the exact same textbook on Amazon. So those are going to be strongly correlated with each other. One number on this list corresponds to one specific particular number on the other list. So how do I analyze data like this? We take the differences. Since the data occurs in these strongly correlated pairs, what I want to do is subtract each pair of numbers and find the difference, what I get when I subtract each number from the other one. Then I treat these differences as just one single sample of numerical data. Now I ignore the original two lists of numbers. Now I just have one list of numbers, which are the differences. Our sample size is now the number of differences we've got. I find the average differences, the X bar of my list of differences. I find the standard deviation from that list of differences. Usually in this case, what I want to do is I want to know if is there really any difference at all? Or is there any statistically significant difference at all? I'm never going to get X bar of exactly 0, but I want to know, is this within the range of the sorts of things you would get if the average overall population difference was 0? So usually the null hypothesis is simply that there's no difference in the population. So H naught is that mu of the differences is just 0. And then we can use the sample mean, X bar, the differences, standard deviation of the differences to make a confidence interval on what the mean difference of the whole population would look like. So let's do a particular specific example. This was from a really fun article I recently read where the pilot was glide testing a Cessna 152 airplane. So here's the idea. If you're up there in a small one-engine airplane, you want to know, and the engine goes out and the engine fails and you're up there and you want to glide for as long as possible so you can try to get that engine started again. Will you glide longer if you leave your propeller rotating freely? Pilots call that windmilling. Or if you lock down the propeller so it can't move. Now, for a long time, the person who ran the study, she read in various manuals and things that it's better to lock down the propeller. That apparently that produces less drag or something like that. But she couldn't find published, publicly available data to support that. So she did a study. So what she did, she went out, brought the plane up to an altitude of 8,000 feet, stabilized it at a speed of 60 knots, and then glided down with the propeller, either windmilling or stopped. She recorded the amount of time, the number of seconds it took to descend down 800 feet, down to 7,200 feet total, and did this on 27 flights. On each flight, she did it both ways, so tried one time going from 8,000 to 7,200 feet with the propeller windmilling, and then another time going from 8,000 to 7,200 feet with the propeller stopped, locked down, did randomization, flipped a coin or whatever to decide which would be done first. And that way, to get some data, to try to see, does it make a difference? Is it really better? Will you glide farther? Or in this case, will you glide longer? Will it take more time to drop that much altitude if your propeller is locked down? So the first thing we do anytime we have any real data set and we actually want to understand it before doing statistics and hypothesis tests and confidence intervals and that, inferential statistic stuff, the first thing we want to do is play with the data, examine it, study it, learn from it, get inside it. I was able to get the data set, loaded it into R, found the glide times generally, and we're in the neighborhood of 60 to 90 seconds, a minute to a minute and a half. We want to compute summary statistics, the mean, the standard deviation, the 5-number summary. So now we're looking at the differences. So we subtract the amount of time it takes with the propeller locked down minus with it windmilling. Average, we see an average of 9.46 seconds difference, a standard deviation of 19.2 seconds. The minimum difference was negative 5.4 seconds on that day. It was better to have the propeller windmilling. First quartile was 1.9 seconds. Third quartile was 6.8 seconds. Median was 6.8 seconds. Third quartile is 9.9 seconds. And then the maximum, the biggest difference was 101.6 seconds. That's interesting. Look at this. We got all this single digit stuff. And then we got 100 seconds. So next thing we want to do, again, before doing any inferential statistics, we gotta get a feel for the data. We make box plots. We make histograms. Here's a histogram of the differences with the propeller stopped minus windmilling. And whoa, what's going on here? We see a nice little mound-shaped set of data over there around 0 to 10 seconds. So that's fine. That looks good, maybe vaguely normal-ish sort of thing. So we can use t-statistics even though our sample's less than 30. And then, holy cow, we got one data point sitting way out there at 101.6 seconds. That, ladies and gentlemen, is what we call an outlier. Let's talk for a minute about outliers because they happen, and as trained statisticians, each of us needs to have some idea what to do with these crazy outlier points. So in general, an outlier is a data point that looks very different than the other observations. There are some different formal ways that different textbooks define an outlier, but the main point is it's coming from some sort of a process which was not the same process that made the other ones. These tend to pose problems. If I want to do my hypothesis tests and confidence intervals, outliers are going to be a big monkey wrench in the whole problem. So what do you do if you have an outlier? Well, step one, first thing to do is hopefully cross your fingers and check to see if it's a data entry error or something. Did somebody mistype it in? That happens. I mean, hey, let's face it. This is planet Earth. Things are messy here. Data is typed in incorrectly. So cross your fingers and hope that, oh yeah, when I was transcribing this, I mistyped it. That's great. Another common thing is some sort of experimental error when you're gathering the data. Something was very different in this particular case, and it's nice if we can establish that. Now, if so, then we fix the data point or delete the data point if it was just straight out an error. But what if it's not an error? In this case, it wasn't. On the 14th flight, when the propeller was stopped, the plane just glided forever. The glide lasted for 174.3 seconds. That was not an error. That was not a typo. That was not a measurement error. Everything was doing fine. There was just some weird kind of updraft or something going on that day. The second longest glide time, that was only 90.6 seconds. So that glide lasted about twice as long as the second longest of all the other ones. Now, sometimes students want to say, well, it's an outlier. Let's throw it out. Being an outlier, that doesn't give us a license to just throw away any data points we don't like. That's kind of unethical. We can't just throw away data we don't like. The whole idea of science is skepticism, and we got to carefully consider the possibility that we might be wrong. The fundamental assumption of all science is that most people are wrong about most things most of the time, so we got to correct our errors and stuff like that. So if it's not a typo or an experimental error, if it's a real data point, well, we want to try to learn from it. As a general rule of thumb, it's not a good thing when the results of our analysis hinge on one data point. If one data point makes a really big difference one way or another, yeah, we have problems there. It means we need more data. Sometimes it can be useful to run the analysis with and without the outliers. See if it makes a big difference one way or another. Try to understand it. Try to get a sense of why that happened, where it's coming from. If we continue to gather more data, would we get more points like that? Is that telling me something about whatever it is I'm studying? Outlier does not mean throw out data. Probably the most ethical thing to do is run the analysis with and without the outlier. If I'm writing a study, All cards on the table. I'm very upfront about what happened, what I got, and I try to learn from it. And I'm very clear about what happened and what it means. Okay, so let's do it. Let's run the hypothesis test with the outlier. Our null hypothesis is the propeller has no effect on mean glide times. Our alternative hypothesis is whether it's lockdown or windmilling, that will affect it. I would be interested either way. If it locking down the propeller makes you glide for a longer period of time or a shorter period of time, both of these would be meaningful to me. So I want to know deviations on either side. So I want to do a two-sided test here. We'll choose a significance level of alpha 0.05, including the outlier. I got a mean difference of 9.46 seconds, standard deviation of 19 seconds. We've got 27 differences, so we compute the standard error. There's the standard deviation divided by the square root of the sample size. We get a standard error of 3.7 seconds. We use this to compute our test statistic. The difference is between 9.46 was the average difference we got. The null hypothesis says that should be 0. So basically we just have 9.46 divided by 3.7. And we have a t-test statistic of 2.56 standard errors, standard deviations. This is a two-sided test. So I want to multiply, in order to get my p-value, I want to multiply the amount in the tail by 2, since I would have been just as interested if I deviated in a negative sense. So I do 2 times quantity 1 minus pt of 2.56 with 26 degrees of freedom, and I get a p-value of 0.017. Okay, that's less than alpha. That's unlikely. That's not a common result. That's less than my 5%. So therefore, we reject the null hypothesis, including the outlier. We have a statistically significant difference. Now, on the other hand, we really should only be applying t-statistics to either sample sizes larger than 30 or sample sizes smaller than 30 that are roughly normally distributed, you know? With that outlier in there, we can't really call that. So this probably isn't a very good way to analyze the data. If I want to include the outlier, I think I need at least a few more cases. If I exclude the outlier, then it looks at least roughly normal in shape. And so we can do that analysis. Let's see what happens if we go that way. If we exclude the outlier, okay, so like in R, I create another data set. My previous data set was called glide. I'm going to call this glide 1, and I'm going to subset this, and I'm just going to say I want my difference to be less than 90. So I'll just throw out that one data point where I got a really big difference. Still, the null hypothesis is that the average population mean is 0. My alternative hypothesis is that the average population mean is anything different than level. Same alpha of 0.05. My average difference is 5.92, and whoa, look at the standard deviation. Holy cow, that's 5.49. Before, that thing was like 19. That's about, it's now only about 1/4 of what it was before. And so now, when I calculate my standard error, okay, there's my standard deviation, 5.49 divided by the square root of 26, that's 1.08. Again, that's almost as small as 1/4 of what we had last time. Now again, we have a smaller difference. It turned out that one outlier actually helped accentuate the overall difference. But even though my difference is smaller, my standard deviation is way smaller. So now I get a t-test statistic of 5.48. That's big. 5.48 standard deviations away from the mean is a big difference. So now when I compute my p-value, 2 times quantity 1 minus pt of 5.48 on 25 degrees of freedom, I get 0.000011. So this is very strongly statistically significant. P-value, yep, that's less than alpha. That's a whole lot less than 5%. Therefore, the null hypothesis, these results like these would be really, really, really unlikely to happen if the null hypothesis was true. You know, if the null hypothesis is true, it doesn't matter one way or another whether the propeller is locked down or not. If you were, essentially the null hypothesis says if you were to do this study again, you'd be just as likely to get the difference going the other way. Have about a 6-second difference in the differences with it being them being longer with the propeller windmilling. That's what the null hypothesis says. So this is really unlikely in that case, and so we reject the null hypothesis. We have a statistically significant difference. All right, let's make us a 95% confidence interval. So we take our average difference that we find, add or subtract the margin of error of this. We're going to do this with the outlier excluded as well, because t-statistics don't apply on samples less than 30 unless they're, decently normal-ish in shape. So what do we want to do? First, I need to find the critical t-value. So I want a 95% confidence interval. That means 95% of the distribution is in the interval. 5% is outside of it, 2.5% in the left tail, 2.5% in the right tail. So I can do QT of 0.975 on 25 degrees of freedom, or because it's a symmetrical distribution, I can find the t-value for the negative tail. I can do minus QT of 0.02525, and both give me the exact same answer, which is 2.06. Therefore, my margin of error is 2.06 times the standard error. So there's my 2.06 times the 5.49 over the square root of 26. Margin of error of 2.22 seconds. So I take my sample mean of 5.92, the mean difference, and I add and subtract 2.22 seconds, and I get, okay. So we have a confidence interval that ranges between 3.7 seconds and 8.14 seconds. We are 95% confident that the population mean, again, if this were study were done 1,000 times, 10,000 times, and then they took the average of that. We're 95% confident that the average of that would be in this range, somewhere between 3.7 seconds and 8.14 seconds. In other words, okay, let's put the context in this. We are 95% confident that in a Cessna 152, while gliding down from 8,000 to 7,200 feet, locking down the propeller will increase the mean glide time by between 3.7 and 8.14 seconds. Now, this is unquestionably statistically significant. That p-value we got there was really, really, really statistically significant. No question about it. But is this practically significant? This is an interesting thing. Now, yes, we can reject the null hypothesis. It would be incredibly unlikely to get a sample like that if whether or not the propellers locked down would make no difference at all. But just because we have a statistically significant result, that does not necessarily mean that our result is of practical significance, useful significance. In this particular case, does that really make a difference? When you're gliding, down, your engine is conked out and you're trying to glide as far as possible, and you're doing a glide where it's going to take, I don't know, a minute or a minute and a half. Is 3, 4, 5, 6, 7, 8 seconds, is that going to make a big difference? Our p-value was highly significant. I'm not so sure that while this is of statistical significance, I'm not sure this is of practical significance. So let's consider this. Our mean glide time, average glide time, while windmilling was 71.6 seconds. That confidence interval says locking that propeller should give us an extra 3.7 to 8.14 seconds. What kind of a percentage increase is that? 3.7 divided by 71.6 times 100 to make it a percent gives us, that's a 5% increase. The other end of our confidence interval would give us 8.14 seconds divided by 71.6 times 100 to make it a percentage, and that's an 11% increase. That's not nothing. We didn't find there was a 1% increase, but that's really only a pretty small difference. 5 to 10% probably. You'll increase your gliding time. Now, I suppose if you're in an airplane and the engine is out, you want every possible second you can get. So lock down that old propeller. But on the other hand, that's not going to make a world of difference. The practical significance on that looks pretty minimal to me. Even though it's highly statistically significant, the practical significance looks kind of marginal. All right, quick summary. Sometimes we have two samples of numerical data, and the data in the two samples comes in strongly correlated pairs. When this happens, what we want to do is we want to subtract them. Take the differences between the pairs, subtracting one from the other. Often it's going to be a final minus initial sort of thing. And then we want to treat that list of differences as one single sample of numerical data, and then we can do our hypothesis tests and our confidence intervals based on that one sample of differences. Before you ever do any kind of hypothesis test, confidence interval, always play with the data, examine it, study it, learn from it. Just get a sense of what's going on using summary statistics and histograms. Always be on the lookout for outliers. These are data points that they're pretty different than all the others. They seem to come from a different process than whatever created the variations within the rest of our data points. And they pose big problems. They require us to think hard. Just because it's an outlier doesn't mean we can throw it out. But after checking to see whether it's just a typo or something like that, see if you can learn from that. See if you can get some insight into what's going on and where they come from. And the final note is just because you get statistically significant results doesn't mean that your results are of any practical significance at all. It's totally possible to get a result where it's highly statistical significance, p-value of 0.000001, that kind of stuff. And yet the actual result that we find, the actual difference we find, the effect size of this is pretty marginal. That happens too. Then we should always be aware of it. Not just assume that because we're highly statistically significant, we found something really important. We may be on the other hand, we may be really sure that something of rather minor importance has been found.